Greetings everyone. Welcome to our presentation titled Implementing Conditional Cleanup After Regression Testing in HPCC Systems. I'm Goutami Sooda.
I am Arya Vinod.
I am Ahana Patil.
And I'm Chandana S.
We're all second year computer science students at Arya College of Engineering. This academic project was carried out under the guidance of RVCE professors Dr. Jyoti Shetty and Dr. Shobhaji and HPCC Systems mentors Attila Vamos and Hugo Watanuki. We would like to extend our sincere gratitude to them for the support, guidance throughout the project. Followed by us, there's another presentation lined up titled Data 360-degree using HPCC Systems by Dhanush and Shreyas. Do watch till the end. Now let us look into the agenda of the presentation. Initially, we will have a brief introduction to the regression test engine in HPCC Systems. Later, we'll look into the need of conditional cleanup parameter in RTE. Then we'll have a detailed look into the working of the cleanup module, ranging from extraction of work unit details to deletion of work units through HTTP requests, and even we would cover the custom logger system in cleanup module. Later, we will have a demo of the cleanup module in local and cloud environments, followed by the benefits of cleanup module for developers. Now, let us look into the regression test engine in HPCC Systems. Whenever a software code is modified or any new feature is added, a special suite of testing is carried out to check against any breakdowns before pushing the code into production. In HPCC Systems, we have our own regression test engine that runs these regression tests. The regression tests are basically a set of multiple ECL queries, which is run across various clusters, namely Thor, HTHOR, and ROXY within the HPCC systems. This results in generation of approximately 3,000 work units. Now I hand over the presentation to Chandana.
Let us look into the need for automated cleanup. During the regression testing process, each test case generates a work unit that records the outcome of the test. Over time, these work units accumulate, potentially creating a large volume of data. Approximately 3,000 work units can be generated during a typical regression testing session, leading to consumption of memory and storage resources. In local development environments, the accumulation of work units can lead to memory issues, slowing down the system and reducing system efficiency. In cloud environments like Azure, AWS, etc., the storage of these work units can incur significant operational costs, impacting the budget and resource management. Unmanaged work units can lead to unnecessary cost and inefficient use of resources. Implementing an automated cleanup mechanism is crucial for maintaining cost effectiveness and efficient resource management within the HPCC systems. Coming to what is the cleanup parameter? The cleanup parameter is a configurable option within the regression testing engine that allows developers to automate the deletion of work units generated during the testing process. The cleanup parameter ensures that work units do not accumulate unnecessarily after each test run, thus preventing the overload of storage systems. Next, we can look into the cleanup parameter supports 3 modes, each serving a different purpose. None is the first mode. This is a default mode. The purpose of this is it retains all the work units generated during the regression test, regardless of the pass or fail status. The next one is the passed mode. This deletes only the work units generated by past test cases, retaining failed ones for further investigation. This can be it's useful for developers who need to focus on debugging failed test case without clustering their systems with the successful test work units. The third one is work units mode. It deletes all the work units generated during the regression test, regardless of their pass or fail status, but retains DFU work units and logical files. The use case is it balances the need for space saving while keeping essential data like DFU work units and logical files. So by providing these options, the cleanup parameter allows developers to manage their testing environment efficiently, ensuring that only necessary data is retained while unnecessary work units are automatically deleted. Here, we can see the workflow of the cleanup module. This is the command line setup. Command line arguments are set up for cleanup parameter of the regression testing engine. Then the mode of the cleanup parameter is taken through the command line interface by the user as input. The date and time of the current RT execution is obtained. This can be seen in the upcoming slides. Looking into the integration to the RT workflow. The cleanup parameter is integrated as a subcommand within the RT's command line interface used when executing a regression test. The cleanup parameter value is passed as a command line argument along with the ECL command to run the regression test. The cleanup module automates the deletion of work units from both local and cloud systems and logs the operation of deletion through a customized logger module. The cleanup argument is added to the run and query subcommands of the RTE using the add argument method as seen in the code snippet here. This method defines the available options for the cleanup operation, such as work units passed and none. The example usage is shown here, wherein the hyphen cleanup work units triggers deletion of all work units and the passed does only the passed work units deletion. After the main RTE operation is completed, the script checks if the cleanup argument is present. If cleanup mode is set to none, the script logs that automatic cleanup has not been enabled and skips the cleanup process. If a cleanup mode other than none is specified, the script initiates the cleanup routine by calling cleanup.doCleanup. So the start time of the RT operation, whether it's query, setup, or run, is recorded using the start time is equal to datetime.now as seen in the snippet here, before the main operation begins. This timestamp captures when the RT operation starts, which is crucial for identifying which work units were created during the specific execution window. The doCleanup function is passed to the log directory, the cleanup mode, and the start time. The cleanup process then identifies and deletes the work units that were created during the specific execution window from start time to the current time based on the chosen cleanup mode. Now I hand over the presentation to Arya.
Now that we have seen how the cleanup mode is passed in the command line interface by the user, in this part of the cleanup module overflow, we shall see how the log files containing the work unit details are identified from a directory. The path to the directory containing the log files is present in a configuration file. The configuration file is read and the path to the log file directory is extracted. Once we arrive at the directory, we encounter configuration files and log files, which can be differentiated based on their file extensions. Based on the clusters on which the RT is executed, we obtain log files with the naming convention as shown in the example. We find that there is a clear definitive pattern to the name. It is the name of the cluster, followed by the timestamp in that specific format, followed by the .log extension. We use the glob.glob function over regex patterns to traverse the log file names and search for this particular pattern. Glob.glob is cross-platform and specifically designed for file name matching. It uses simple wildcard patterns and can handle different cases such as path separators based on the underlying file system or operating system. On the other hand, regex patterns are for general purpose string matching. They are complex and time consuming as they are not optimized specifically for the purpose of file name matching. As we traverse the file names, we also use the start date and time of the execution of RTE to consider only those log files created any time after that timestamp. We have handled the case where there may be ambiguity in the exact timestamp should it take place at midnight using the time delta function between datetime objects. Finally, upon identifying the log files that satisfy the naming convention and timestamp, the log file is sent as an argument to the next function in the cleanup module. Over to you, Ahana.
Now that we know how among all other numerous files, the right files to be deleted are extracted, I shall further explain how the work unit ID and URL are extracted according to the input cleanup mode and how these URLs are modified to perform deletion using HTTP post requests. Let us first look at how the extraction of work unit URL works. To the left, you can see the flowchart for this purpose. The idea is to create a function that runs through the contents of the input log file and save each line of the file in a list. Further, we see the input cleanup mode is all. The URLs of all work units are extracted. Else, when the input mode is passed, URLs of only passed work units are extracted for deletion. Let us have a look at the Python code for this purpose. The function is named getWorkUnitDetails, which takes two inputs. One is the log file, which has the URLs to be extracted, and the other input is cleanup mode. Each log file is opened in read-only mode. Then there can be seen another function definition named extract_URL, which is designed to return the URL string. Now, if the input cleanup mode is work units, for each line, extract_URL function is called to check and extract the URL. Otherwise, when the cleanup mode is passed, first the presence of pass string is checked to make sure the particular work unit is a passed one, and then the URL is extracted from the new line. Finally, in both the cases, the extracted URL string is further passed as a parameter to delete work unit function, which we shall be looking into a little while later. Here, we can see a log file containing the log status of various work units. It contains the work unit IDs and URLs. These URLs shall be extracted as mentioned in the previous slide and further be used for deletion using HTTP post requests. Now, let us look at the delete work unit functions, which is responsible for the deletion of work unit pertaining to the input URL. Firstly, the input URL is modified to make it a deletion URL by replacing a substring from the URL. Now, try and accept block checks for the response and handles the errors properly. The result of this deletion process is printed on a terminal and recorded at different log levels based on the deletion status, with the work unit ID of the associated work unit. This is how we check if the work unit was deleted or not. Another way is to check whether the work unit still is in the ECL watch interface. All this will be shown in the demo in the end. Over to you, Goutami.
Coming to the last stage of the cleanup module, we have a custom logger system that helps in recording the status of work unit deletion. Now let's have a closer look into its working. The custom logger module generates log files that serve as a tool for debugging and is useful to check the status of work unit deletion. To the right, we have a code snippet. Here, we define a logger instance named cleanup and a class named serial number formatter. This class initializes and prefixes a serial number to every record in the log file, basically every log message. The build cleanup logger function sets the default logging level to info and creates the log file following standard naming conventions in the log directory using the OS module in Python. It also sets the serial number formatter as the formatter class for the cleanup handler associated with our cleanup logger instance. To the left, we have a sample log file that has been generated by the cleanup module. We can see that the log file records the successful or failed status of work unit deletion along with the work unit URLs when necessary. Now, let us look into the various logging levels used by the cleanup module. Firstly, we have the info level, which is used to log general information about normal operations. In our cleanup module, it is used to log the successful deletion of work units. Next, the debug level is used to log diagnostic information for debugging purposes. It is used to indicate that automatic cleanup routine has not been enabled. The warning level is used to log information that might require user attention or action. Here, it is used to log the message indicating the start of cleanup module execution. Lastly, the error level is used to log serious issues that require investigation, like failure of work unit deletion. Now, let us see the cleanup module in action with a demo in both local and cloud environment. Let us first look into the working of the cleanup module in the local version of HPCC Systems. Here, with the start command, we initiate the local version of HPCC Systems in a Ubuntu VM. We see that the various clusters are starting like DALI, DFU server, ECL agent, etc. Now let us run the regression test engine using the ECL test command. Here we're using the query command in order to run the test only on 3 test cases, namely action 1, 2, and 5. We have set the target cluster to HTHOR and the cleanup mode has been set to work units. In this mode, we would see that all the work units would be deleted irrespective of their test case has been passed or failed. Actually, ECL test has 3 different modes: run, setup, and query. Here we have used the query command. The run command could be used to run the entire test suite, and setup is used initially to set up everything. Here, if we see, we can see that the automatic cleanup routine has been invoked, as well as all the work units have been deleted successfully. Now we can check the log files that have been generated by the regression test engine. This is the log directory wherein the regression test engine's original log files are generated. The hthor.date.log file is the one that is being parsed by the cleanup module in order to extract work unit URLs, as explained by Ahana. Further, we have custom cleanup log file that has been generated by our cleanup module that logs the deletion status of each work unit. This is the same output that was printed on the terminal as well. Now, we can check the status of work unit deletion using the ECL Watch web interface. For that, we have just copied the work unit ID. When we search for this work unit ID in the ECL Watch, we can see that it will give not found status, which means the deletion was successful. Now let us try out the other modes of cleanup. We can try out the mode passed. As explained before, in the passed mode, we would only be deleting the work units that have been generated by past test cases. Let's limit the cleanup regression test engine to just one test case, that's action5.ecl. That would save our time. And we see that the work unit has been generated and our cleanup module has been invoked and the work unit has been deleted as well. Now coming to the other mode of cleanup, that is none. In this case, the cleanup module will not be invoked. It is similar to not passing any cleanup parameter itself. By default, the cleanup mode would be none. Here, the work unit has been generated, but we see that the Sooda destructor has been called directly without calling any cleanup module. Now let us quickly switch to the cloud version of HPCC Systems. Here, we have used minikube in order to mimic the cloud environment on the local system. Using the start command, we have started all the Kubernetes clusters. Using kubectl getpods command, we are just checking out the running state of all the pods within the cluster. The next command, minikube service ECL Watch, lists out the URL of the cloud version of ECL Watch, which is hosted on a different port and IP address, unlike the local one. The interface remains the same. Now, we have the command for the regression test engine already run here. The only difference in the command comes with the server and config being specified explicitly. The server has been specified as the ECL cloud version's IP address and port number, whereas the config file has been defined as ECL test azure.json. The cleanup mode being passed is work units, and we are restricting the query to just a single test case, action1.ecl. Since we have not specified the target cluster explicitly, we see that it has been run on all the three clusters, Thor, HTHOR, and Roxy. Hence, 3 work units have been generated as well as the cleanup module has been invoked and the deletion has happened. Let us see the working of cleanup mode in other modes, like let's try out passed mode. We have been using the same cleanup module for both local and cloud environment. The working and functioning remains the same, just the commands to execute the routine is different. Here we have just set the target cluster using -t command to Thor. We see that one work unit has been generated as well as it has been deleted successfully. Similar to the local environment, we can again cross-verify the deletion of work units. We can just copy the work unit ID and paste it over the ECL Watch, the cloud one. And we would again see the status of deletion to be status of work unit to be not found. Yes, that means the deletion was successful. So we come to the end of the demo.
This is a tabulation to visualize the effect of adding the cleanup parameter to the regression test engine. For these results, the RTE was executed in a system containing many log files which hold information of a large number of work units. The runtime of the RTE with and without the cleanup parameter have been compared on each cluster individually and together. As can be seen, the latency is not over 8 to 15 minutes, which implies that the deletion operation took barely a few milliseconds per work unit. An interesting point to note is that the final column shows that around 3,000 work units have been deleted in 15 minutes. This shows that while the purpose of the cleanup module has been to optimize memory usage, it has not compromised the time efficiency of the RTE by much. Here we have the advantages and outcomes of integrating the cleanup module with the RTE. It has automated the process of deletion of work units, which was previously performed manually using the ECL Watch interface. It can delete any number of work units based on the mode of cleanup and has not added much overhead to the functioning of the RT, proving it to be efficient and reliable. It has been designed in such a way that it can be extended to automate deletion of other types of files and metadata if required, proving its scalability. With this, we come to the end of our presentation. We hope this talk has helped you understand and appreciate what we have tried to achieve by contributing to the HPCC Systems regression test engine codebase. Thank you for your time and attention. Stay tuned for the upcoming presentation.
Greetings. I am Shreyas Shankar and this is S. Dhanush. We are third year students at the Department of Computer Science, RV College of Engineering in India. Our project is titled Data 360-degree View using HPCC Systems. Before we begin, I would like to mention all the people who have aided us in this project. Firstly, I would like to thank all the student contributors for being a part of the project. Next, I would like to thank Dr. Jyoti Shetty and Dr. Shobha Ji of RV College for their invaluable guidance. By extension, I would also like to thank the LexisNexis team who provided a cluster and tech support. Finally, I would also like to thank Mr. Shravan Talpula and Mr. Ravi Joshi of ProfitOps AI for their mentorship and support. This project was done in collaboration with ProfitOps AI, a company headquartered at Georgia, USA. Having a team with about 50 members, the company was founded by Mr. Shravan Talpula, who is also the CEO of ProfitOps AI. The core product of the company is a unified decision intelligence platform used by business leaders to enhance the enterprise decision-making process. It is used to help businesses, especially in retail, to safeguard their profit margins. ProfitOps uses real-time monitoring, anomaly detection, and data-driven insights to proactively identify and address revenue and operational leakages. They also centralize profit protection efforts and provide clear accountability and actionable insights to their end users. The project itself is a research into analyzing the feasibility of integrating HPCC systems technology into the ProfitOps AI tech stack. Various existing technologies such as FTP, MongoDB, AWS, and MySQL were used for data inflow and outflow to the HPCC systems platform. After positioning the data into the HPCC cluster, the next stage of the project was focused on mimicking OpenRefine's features using ECL. For context, OpenRefine is a Java-based open source tool for working with large and messy datasets. It is favored by data analysts and researchers alike due to its rich options. Now, the question may arise, why choose to mimic OpenRefine on HPCC? The simple answer is, we want the best of what HPCC and OpenRefine have to offer. HPCC has already established itself as a big data platform specializing in distributed data storage, querying, and analytics. However, OpenRefine has a greater emphasis on data cleaning and transformation. Therefore, by mimicking the functionality offered by OpenRefine, that is, the ability to clean and transform data on a much larger scale by leveraging HPCC systems power, we can enhance an enterprise's ETL processes. Now, coming to the final stage of the project, a POC titled Data 360-degree View was prepared. Using the results from the earlier stages, this final project accepted input data from Omni data sources, performed OpenRefine-like transformations on the data, and outputted a configurable unified schema. This is the high-level overview of the project. As we go deeper into the presentation, we shall further understand the exact results achieved by the team.
Hello all, I am Dhanush. I am currently pursuing my third year in computer science engineering at RVCE along with Shreyas. So today, I'll be continuing with data ingestion into HPCC Systems platform. But wait a moment, I would like you guys to assume whatever is built as a software product so that you understand things that we talk about here more clearly and it will be more conceivable. So jumping on to the points. So main point to note down is that we need to perform some operations on data. So where does the data come from? For a user to work on the data, he or she needs to import data from some platform. So discussing this, we land on our first stop, that is SQL, mainly MySQL. So HPCC provides us with a MySQL plugin, making it easier for the team to build a generic function as possible. Function was created to read the structure of the data set, which needs to be spread into the HPCC system cluster. Functions that were built in these aspects were creating a new table in MySQL, then inserting some contents from a CSV and XML files which are stored in an HPCC cluster to MySQL table. So there's some connection between a CSV and the MySQL table directly with an intermediate being HPCC, then storing some contents of MySQL table to a logical file in HPCC cluster. Then the fourth one is deleting contents from MySQL table itself. So truncating. Deleting might be a better work, but truncating, then deleting the MySQL table itself. So some of the functions implemented were incremental data push and full data push to the HPCC system cluster. So here is an example of an incremental data push where few of the data are ingested later on in the ongoing process. Like here, we can see that order V1 CSV is ingested into the HPCC system cluster beforehand, and later on the further dates, so another order V2.csv is inserted. So it will be treated as version 2. The previous one would be version 1. So here a continuity of a version is maintained. So this is all about MySQL or SQL. Then coming on to the second stop, that is MongoDB. So we need to have some import from MongoDB also. So again, this is similar to what I discussed in MySQL. So here the HPCC provides us with a MongoDB embed functionalities. And here also we need a connection between MongoDB cloud and the HPCC cluster. So here also there will be CRUD operations which will be undertaken. So here the main point was the version controlling. So to keep a watch, so to keep a cron job, a kind of cron job watch, we had something called as cron job. So it was built independently of HPCC to have an like watch over the updations which occurs every time. So coming to the next topic.
With the rise in popularity of cloud computing, Profitops AI was interested in assessing the effort and methodology required to integrate contemporary cloud storage solutions with HPCC systems. For this task, AWS S3 service was chosen. S3 uses buckets which serve as a container to store files or data. These buckets serve as top-level storage units which control how data is accessed and managed. Data input from an S3 bucket to ECL landing zone was achieved by using an ECL file which was constantly running the AWS S3 sync command. ECL landing zone files were then converted to logical files by using the DFU plus spray command. Working with CSV files was very straightforward. All we had to do was use the DFU plus command directly. However, when working with JSON or XML files, the method used was slightly different. When working with JSON or XML files, the very first step is to spray the landing zone files as CSV logical files. After this, we defined a record structure containing two entries: file name representing the actual logical file name and data representing a string containing the actual JSON or XML data. After this, we use the respective JSON parser or XML parser in ECL to extract the required data and store them once again on the cluster as logical files. After we obtain the logical files from the above steps, some transformations will be performed on the data and the result would be stored back to the cluster as logical files. To bring the transformed logical files back to the S3 instance, scripts were used to despray the files. Following this, the landing zone was synced with the S3 bucket to achieve data outflow. Now, we notice that both data inflow and outflow rely on syncing the landing zone to S3 bucket. This can be made more efficient by using mount point for AWS S3, where a local directory is automatically synced to the S3 service without constantly running the AWS S3 sync command. On the next task, research on how to transfer data from and to the HPCC cluster using file transfer protocol was also researched. For this task, an Ubuntu system was installed with an FTP server. Specifically, we had used the VS FTPD server, which is one of the fastest and most secure FTP servers for Unix-like systems. This server was responsible for pushing data from the Ubuntu machine to the HPCC cluster. Please note that the data is pushed into the landing zone of the HPCC cluster. To actually use the data, it has to be sprayed into the cluster using the dfu plus command we just mentioned in the previous slide. Furthermore, if your input data is within some other Windows or Mac machine, transfer of files to the Ubuntu machine could be achieved by using FileZilla, which is an open source cross-platform FTP application.
So till now, whatever was spoken of was about functionalities developed to import and export data. So precisely, data might be misleading. So let's take it as structured data. So now this data might not be recognized or categorized into data type. So, or we need to define a record structure to be precise. But this is not the case over here. So we consider all the entities of the data to be string so that no data loss is faced as a consequence. Here, all the data transfer operations that we use here is similar to the one which is present in OpenRefine. So we went through the GitHub. It's an OpenRefine is an open source like localhost setup where you can find all the codes. So we went through all the Java code and converted back into ECL. So the first option that we gave was transform operations using HPCC built-in functions. So HPCC system provides us with built-in functions and is well documented and made it easier to go through all of them. And we were able to fix the puzzle with the best suited built-in function. These are the transform operations that were enabled. So trim leading and trailing white spaces, then collapse consecutive white spaces to reduce the string length, then unescaped HTML characters. So basically here we have something called special characters in HTML. So for white space, it displays as and, NB, SP, semicolon. So these are all the characters which will be replaced by an ASCII corresponding like character. Then here we replace the smart code with an ASCII. So in the right side, you can see an example where you can, in the second and in the fourth, you can see there are some smart codes. So which won't be available in ASCII form, like code. So that will be converted into ASCII format. Then we have common case transforms, whether to either uppercase or to a lowercase. So the second option was recognizing and converting and formatting date and time. So given a time or a date in any format should be recognized and it should be converted into a common format. So here for time, we chose the common format to be unsigned int. It will be represented as a HHMMSS. So, and for the date, it will be YYYMMDD. So here we didn't apply the built-in functions directly. So we built a pre-processed Python embedding function, so which enabled a flexible processing of the data, and through that we were able to create and formatted time and date. So the first example was to import a like data called as like money, currency. So here an example is $20.1, which needs to be converted into a decimal. Basically, when we import this, it will be either converted to 0 or a 1. So it is an basically defined as an error. So this needs to be avoided. So we take it as a string and convert it basically into a decimal later on. Next stop is converting from rows into column. So we need to transpose rows into column. So here we input two indices precisely. So here if we give the indices 1 and 5, so between street and country, as you can see in the left-hand side of the table, so we collapse all the columns from 1 to 5 into a single column. So as you can see in the address column. Similarly, this might be a little bit overhead to define indexes. So we came up with an like another strategy. So where we used an HPCC Systems library, standard library called as get data patterns. So using that, we were able to give an input as a street and country itself. So all the columns in between street and country, including those two, will be collapsed into a single nested column, and it will be output as an XML. Actually, the right hand side will be displayed as XML, and it is the representation of it. So here we have another row into column, or you can either call it as column into row. It might be ambiguous to call any to choose any of the word. So here we have something like key column pair. So as you can see over here in the left hand side, so we have the name, street, city, state, country, and postal code. So we transpose this to column, and you can see in the field name, we convert the field names into key and the value inside the cell as a value in the table, in the output. So here we need to choose a column. So name as a column, which is kept as a separate, like it should not be modified. So for that, again, we used HPCC Systems get data patterns. So here is another option where we can find all the key values represented in a single column. So key will be separated with the value by a column. So it will be detected and it will be transposed into another table as shown below. So here the order and the prerequisite format of the data is compulsory, and given the data in the right format, the desired output will be achieved. So coming to the next option, it is a key value column. So similar to the previous one, here also, instead of keeping it in a single column, we divide it into two columns, field and a value. So key and a value. So here again, we have a field column and the second column will be a value. So here as well, the order of the row matters, and a missing row will be considered as null or an empty cell itself. So hereby I convey all the test cases, that is very few crucial test cases, and I hope the idea and the concept is conveyed.
Till now, we have looked at various methods for data inflow and outflow to HPCC systems. We have also looked at various transforms resembling OpenRefine's functionality, but developed using ECL's pre-made libraries and some of our own application code. Now, these are all like individual pieces of a puzzle. Alone, they're not that powerful. However, they can be assembled into something bigger and greater. As a capstone project, we considered one of ProfitOps AI's use case. They work with multiple data sources with different schemas and originating from different systems. They needed a method to cleanse all their input data and then derive a customizable unified schema that combined all the input data into one big file. Let us explain with an example. Consider the use case where we are dealing with multiple customer orders. These orders are tracked using three different sources. An order details, a JSON file containing information for each order, including customer details, order date, order status, and a list of items. The shipment details are XML files containing information for each order, including the number of packages, package tracking numbers, and delivery status. Finally, the shipment costs, all of these are CSV files, contains an exact breakdown of the shipping costs. Input data shall be fed into the HPCC platform using the methods described in data ingestion. Perhaps some of your CSV files are stored as SQL tables. Perhaps some of your JSON files are stored in MongoDB. Perhaps your S3 bucket has a portion of all the required files. We bring all the required files to the ECL landing zone and then spray them into the cluster using the dfu plus command. Following this, we need to combine all our input files into a singular output file having a configurable schema. Considering the current example, we notice that the order details JSON file is connected to the shipment details XML file using the common identifier order number. Similarly, The box ID parameter of shipment details file is mapped to the package identifier field of the shipment costs file. The final output file should resemble a JSON file, and it is an amalgamation of all the input files. This final output file is what we call the unified schema. Let us now discuss the exact methodology. By this stage, we assume that all logical files are present and accounted for. To derive the unified schema, we first need metadata on all our input files. During development, ProfitOps had provided us the Spark metadata we needed for the project. At this stage, they had also given us the metadata for the final unified schema. We had developed a Python script to generate ECL record structures using the given Spark metadata. Now, after generating the ECL record structures, the next task was to group logical files having the same record structure together. This was achieved by following fixed naming patterns for data inputs from different sources. Let us take an example. If we have 3 shipment costs files and 2 shipment details files, the logical file names for the shipment cost file would be shipment cost 1.csv, shipment cost 2.csv, shipment cost 3.csv, and so on. Notice that the prefix and suffix remain same for similar files. We only change the number in between. This is used to account for the automation that we had provided. Next, the grouping was achieved by using ECL logic. Files with similar record structure would be loaded into the same dataset for processing. Now, after performing data cleansing and transforms, we shall start creating the unified schema. Do remember in the example mentioned in the previous slide, there is a link between different data sources using certain common attributes. The precise linking is achieved by an ECL file using ECL transforms. Modifying this linking is how you achieve a configurable unified schema. After the linking is done and the final dataset is prepared, it is outputted back to the cluster as a logical file and then desprayed to the landing zone. Now, the file is ready to be used in any application logic. It can be brought out of the HPCC cluster using the outflow methods discussed in the data ingestion section. With this, we have come to the end of the presentation. Thank you, and I hope you enjoyed the session.
Thank you.